An image of Jupiter's southern aurora, obtained by the Juno Ultraviolet Spectrograph UVS instrument on the 2nd of February 2017. This image overlays 3 different UVS wavelength ranges and color codes them such that red, green, and blue indicate high, medium and low energy electrons impinging on the atmosphere, with color mixtures indicating a mixture of energies. The streak on the upper left is the auroral tail caused by Jupiter's moon Io. Credit G. Randy Gladstone. What's powering the powerful auroras at Jupiter's poles? New results suggest it's not the same mechanism powering the most energetic auroras on Earth, contrary to scientists' expectations. Jupiter's auroras are hundreds of times more energetic than those on Earth and don't radiate in wavelengths that are visible to the human eye. But both Jupiter's and Earth's light shows are manifestations of the same fundamental phenomenon: accelerated particles colliding with atoms in the atmosphere, releasing energy in the form of light. Which is why researchers with NASA's Juno probe expected to find evidence that the charged particles that create Jupiter's auroras get their energy via the same mechanism that drives high-energy auroras on Earth, according to Barry Mock, a scientist at the Johns Hopkins Applied Physics Laboratory and a member of the Juno collaboration. A complete reconstruction of what the northern and southern auroras on Jupiter looked like to the Juno Ultraviolet Spectrograph UVS as NASA's Juno spacecraft made a close flyby of the planet. Jupiter is represented as a digital model as it might be observed in visible light. Credit Bertrand Bonfond. In Earth's atmosphere, auroras are created when the sun showers the planet with a stream of charged particles known as the solar wind, which are pulled toward the poles by the magnetic field that wraps around the planet. The motion of charged particles along those magnetic field lines creates electric currents in the space above Earth's atmosphere. This activity also creates electric potentials. Think of them like power-up stations, where any charged particle that passes through gets an energy bump and is accelerated. If one of those accelerated particles comes down into the atmosphere and collides with an atom, the collision will cause enough energy to release visible light. This mechanism is responsible for the planet's most energetic auroras, which create those stunning light shows for viewers on the ground. When a particle detector maps the particle energies around a powerful aurora, the researchers expect to see a peak where an electric potential is located. Mock said they call those peaks inverted verses, because that aptly describes the shape of the data line on the graph. An image of Jupiter's auroras left combined with electron measurements showing inverted verses that indicate a discrete particle acceleration process near the planet's auroras. However, researchers did not see the inverted verses during all of Juno's intense aurora flybys. Credit G. Randy Gladstone. When the Juno probe began making close flybys of Jupiter, the spacecraft began collecting particle data with an instrument called the Jupiter Energetic Particle Detector Instrument JEDI. There is another particle instrument on Juno called Jovian Auroral Distributions Experiment, or JADE, that studies lower energy particles involved in the aurora. Mock, who is principal investigator for the JEDI instrument, said researchers did see those inverted verses in their data, indicating these discrete electric potentials were accelerating particles above Jupiter's atmosphere. In one sense, this is a very simple result, because we observed huge electric potentials, Mock said. We've seen potentials of up to 400,000 volts, which is 10 to 30 times larger than what's been observed in Earth's aurora. And yet, the results still puzzled Mock and his colleagues, because the inverted verses appeared in only about 50% of Juno's flybys of Jupiter's most intense auroras. They simply couldn't be responsible for creating all of those intense auroras, even though this mechanism is responsible for creating Earth's most energetic auroras. Auroras over Earth. Amazing northern lights. Photos from space. Juno's orbit around Jupiter brings it close to the giant planet every 53 days. During those close flybys, the probe can be traveling at top speeds of 55 kilometers per second, or more than 123,000 miles per hour, 198,000 kilometers per hour. As a result, the instruments may be able to collect that over the auroras for only about 2 seconds, Mock said. The authors noticed the discrepancy between their expectations and what the data showed them after the very first science flyby. In their new paper, they confirmed those findings based on data from 4 science flybys. Based on their measurements of particle energies around the auroras, the authors think it's likely that, rather than getting boosted to a specific energy level, the particles are being gradually accelerated to a wider range of energies. The mechanism is what the authors call stochastic acceleration or turbulent acceleration, and it is responsible for creating some of the weaker auroras in Earth's atmosphere. Typically, these auroras are not visible to the human eye. In turbulent acceleration, the particles are essentially catching a ride on waves in the plasma that lies just above Jupiter's atmosphere, according to Mock. Plasma is a gas in which the electrons that typically orbit the nucleus of an atom have been freed, or ionized. Like surfers on the ocean, the particles are accelerated by the waves. The wave exchanges just a little bit of energy with the electron. And then the electron goes on to exchange energy with another wave. And slowly but surely the particle gains a huge amount of energy by interacting with thousands of different waves, Mach said. The result of that is a statistical distribution of energy. Some particles have intermediate energy, some have very high energy, so you get a broad distribution of energy. That's what we see in the energy fluxes. Jupiter's northern aurora imaged by the Juno Ultraviolet Spectrograph UVS on December 11, 2016. The left panel false colors the aurora based on overall intensity. The right panel overlays 3 different wavelength ranges and color codes them such that red, green, and blue indicate high, medium and low energy electrons respectively, with color mixtures indicating a mixture of energies. Credit G. Randy Gladstone right image and co-author Bertrand Bonfond left image, but this is still a hypothesis, Mach said, and the researchers aren't sure yet how those waves are generated, if they emerge as a result of the energy potentials or from some other source. Juno's orbit will take it on slightly shifted paths around Jupiter, meaning it will fly over different regions of the planet. The probe's orbit will also allow it to reach lower altitudes over the places where the charged particles are accelerated. Lucky for the Jedi team, Jupiter's auroras are constant, because they are fed by the solar wind as well as a steady supply of charged particles from the Moon Io. Those low-altitude passes could provide perspective that allows the differences between Earth and Jupiter auroras to be better understood, Mach told Space.com. The paper was published online today, September 6, in the journal Nature. Follow Calico Field at Calico Field. Follow us at Space.com, Facebook and Google. Original article on Space.com.